morning, everyone. Myself, Priyansh, currently pursuing BTech from VIT Chennai. I am here to tell you something more about applications of automata theory in game theory. So, without any further delay, let's dive into the topic. In game theory, presenting players' strategies directly affect the performance of the players. Utilizing the power of automata is one way for representing players with strategies. It was found that finite automata, adaptive automata, and cellular automata are widely adopted in game theory. The applications of finite automata are found to be limited to present simple strategies. In contrast, adaptive automata and cellular automata are intensively applied in complex environments where the number of interactive players is high and therefore complex strategies are needed. Introduction. Any problem with interfacing? So let's have an introduction to game theory. Any problem with interacting participants and actions can be treated as a game. When car driver puts a plan to drive in heavy traffic, they are actually playing a driving game. When user bids on bidding-based websites, they are actually playing an auctioning game. In elections, choosing the platform is a political game. The owner of a factory deciding the price of products is an economic game. Obviously, game theory can be presented in a wide range of applications. What is game theory? Game theory is a branch of applied mathematics that provides tools for analyzing situations in which parties that are players make decisions that are interdependent. This interdependency causes players to consider the other players' possible decisions or strategies in formulating strategies. Here we have a video which will make us more clear about game theory. So let's take a look.
Let's assume Sarah promises to give Matt $100 if he runs a mile in less than 7 minutes. In this case, everything depends on Matt. He can train until he consistently succeeds, and when he's ready, he can show Sarah and get his $100. Game theory doesn't study situations like this one. Instead, it studies situations involving more than one participant and in which not everything depends on one person. For example, in the game of chess, the other player's moves continuously influence your strategy. That would be one example of a situation studied by game theory, but don't make the mistake of assuming only actual games are studied. Game theory is also used to, for example, analyze situations in which multiple companies are competing against one another. Just like in a game of chess, the actions of one company are influenced by the actions of the other participants. For example, if a competitor lowers the price, the other companies might be forced to do the same. As you can see, game theory basically analyzes the behavior of two or more participants in situations involving rewards or punishments. The rules of the so-called game are known by everyone, and it is assumed that all players are rational. Now, of course, game theory will never be able to predict human behavior with 100% accuracy. In one situation or another, you might very well do the exact opposite of what game theory suggests, but still, it offers some truly fascinating human behavior insight.
From this video, we got to know that game theory is only applied when there are more than one participant. Game theory is not actually 100% accurate, but it provides some fascinating results which will help us to predict the result more than just a random guess. Now let's have a look on the entities of a game. First of all, we have players, where one side of the game tries to maximize the gain, while the other side tries to minimize the opponent's score. However, these players can be humans, computer applications, or any other entities. Environment. This includes board position and the possible moves for the players. Successor function. The successor function includes the action and returns a list of pairs where each pair indicates a legal move and the resulting state. Terminating state. The terminating state specifies when the game is over and whether the terminal state is reached or not. Utility function. The utility function is the numeric value of the terminal state. Automata types. As the name suggests, automata is a self-operating machine. The output of one automata is the combination between the consequences of the current input and the history of the machine's previous input. An automata is designed to automatically follow a predetermined sequence of operations or respond to an encoded instructions. There are many types of well-known automata, such as finite automata, Turing machine, push-down automata, adaptive automata, as well as other variations such as random access machines, parallel random access machines, and array automata. Finite automata. Finite automata are composed of fixed finite memory, which takes its decision using that finite memory. That is, a finite non-empty alphabet, a transition function, an initial state, and a set of final states. Finite automata can be classified into two types, that is DFA, that is deterministic finite automata, and NFA, that is non-deterministic finite automata. DFA is only permitted to be in one state at a time. On the contrast, NFA can be in two or more states at any given point of time. Finite automata are widely used in game theory. For instance, in iterated n-player prisoner's dilemma, that is INPPD, finite automata can be used to represent players' strategies. The automata states represent the player's action and the input is the strategy profile observed from the other players. Therefore, if n represents the number of players in the game, then the set I is defined as I goes from 0 to n minus 1. The set of states S can be divided into two states, that is C and D, such that the players cooperate or defect if state belongs to C or state belongs to D, respectively. Adaptive automata. In typical learning automata system, a self-operating machine responds to a sequence of actions to achieve a specific goal. The automata in turn may respond based on predetermined rules or it may adapt to its environmental dynamics. In other words, adaptive actions are attached to the state transition rules of the adaptive automata and they are activated whenever the transition is applied by removing or inserting new elements to the automata's transition state. Mathematically, adaptive automata can be defined using a set of 10 tuples, where tuples can be classified into following categories. State tuples, set S, the set of states, I naught, the initial state of automata, F is the final state. Input tuples. This category includes tuples like alpha and gamma. Alpha is the set of input symbols, gamma is the set of parameters and the variables. Transition tuples, where delta is the transition relation, where this relation takes two elements, an element from U and an element from Q. U is a set of adaptive function labels, H is a set of generators, Q is used for mapping parameters, and at last we have set of adaptive actions. Each adaptive action consists of type and the transition of the adaptive actions. The action type can be either a query, remove, or insert action, represented by question mark, minus symbol, and a plus symbol respectively. Adaptive actions are formulated as calls to adaptive function with a set of parameters. These actions describe the modification which should be applied to the adaptive automata whenever they are called. Technically, simple finite automata can be turned into an adaptive automata by following its rules to change dynamically. The following figure illustrates the concept of adaptive automata where the discrete arrow between T1 and C2 is created when the transaction between C1 and C2 is accomplished. Cellular automata. The cellular automata is based on lattice of cells where each cell may be in a predetermined number of discrete states. Updating the states of cellular automata in each time step requires a predetermination process of the neighborhood relation, indicating the communication structure between the cells. Updating the state of each cell is carried out using a transition rule. Each transition rule takes the state of all the cells in its neighborhood as input to the automata and updates all cells in the cellular automata synchronously. For simplicity, the following properties and the characteristics of a given cellular automata. The cells are regularly arranged in an n-dimensional grid. Each cell has an initial state selected from a finite set of states. Update is carried out in a discrete time step. Changing the set of cells depends on the set of local rules. The selected transition rule is applied to all cells. The updated process is carried out simultaneously for all the cells. However, cellular automata are considered easy to implement and, and emulate on a computer. In addition, cellular automata exhibits a wide range of possible non-linear behavior, and thus it is capable of producing output at the highest complexity level for thought of formal language theory. The application of automata in game theory. Automata theory has presented various types of automata with different categories. In this section, we will go through the application which have successfully utilized the concept of automata in game theory. Application of finite automata. Recently, finite automata have been widely used to represent player strategies in game theory. For instance, the researchers of the work mentioned in Go and Stman in 2004 have conducted several experiments, and the results showed that finite automata have significantly improved the performance of n players' prisoner's dilemma. Therefore, the study introduced dynamic systems where agents start the game with randomly chosen strategies which are represented by finite state automata. The agents are allowed to change their strategies during the game. In the Lindgren and Norden's 1994 book, the author have presented a model which utilizes genetic algorithms and finite automata for presenting the strategies of prisoner's dilemma with changeable memory size. The work presented showed the benefits of finite learning automata, which help agents to find the actions that minimize the expected number of penalties received or maximize the expected number of payoffs received. On the other hand, the difference between the environments or representations, the players in lattices, trees, or graphs using ES techniques based on many factors that in turn affect the outcome of the evolution of strategies. Some of the factors, the number of players, techniques, evolutionary computations, and the type of automata and neighborhood structures. However, finite automata are found effective in representing simple strategies in game theory. Nevertheless, game theory is interested in representing simple strategies since many real-life applications do not require complex strategies to achieve their goals. Application of adaptive automata. Adaptive automata-based devices have been presented as powerful tools for defining complex languages. Adaptive automata have the following important features. First of all, the accepting procedure performed by an adaptive automata is done effectively due to their structure, which is based on finite state or structure push-down automata. Adaptive automata can handle context dependencies in a strict syntactical way without the aid of auxiliary semantic procedures. The structure of adaptive automata can be extended to implement the transducer, allowing the generation of parse trees as a side effect of parsing sentences. Generally, adaptive automata have cheaper implementation as compared to other mechanisms. Adaptive automata can be considered as alternative to existing solutions of the natural language processing. In other In order for adaptive automata to do self-modification, adaptive acts adhered to their state transition rules are activated whenever the transition is used. Adaptive mechanisms can be defined as adaptive actions when which changes the behavior of adaptive automata by modifying the set of rules defining it. The simpler notation for representing adaptive automata should have some features such as being at last, compact, simple, expressive, unambiguous, readable, and easy to learn, understandable, and maintain. However, finite automata are the particular cases of adaptive automata if the automata have no rules associating adaptive functions to transitions. The model can be reduced to finite automata. This characteristics is considered important to use adaptive automata naturally where finite automata are required. Applications of cellular automata. Cellular automata can be complex systems by themselves, or they can offer good ways of studying the behavior of complex systems. In this section, We overview the existing models and algorithms which have successfully utilized cellular automata for analyzing or achieving desired dynamics of a complex system. Back to 1975, Alvin was the first person who models the checkboards models as cellular automata. In his book, The Analysis of Complex Socio-Economic Systems, Alvin has shown that cellular automata can provide enormous potential for understanding social dynamics. Kinmet have represented a model to stimulate and solve complex systems. The model is based on cellular automata with some approaches for agents programming, such as artificial intelligence, automata modeling, distributed computing, swarm intelligence, and genetic algorithms. In 2009, the researchers examined how the spatial structure of environment loss affects the eco-epidemic, and they stimulate the heterogeneous lattice landscape by defining two environment states that is suitable and unsuitable. We can conclude that representing the behavior of n players, the prisoner's dilemma model using cellular automata has great benefit since most of the researchers can utilize it to distinguish the effect of neighborhood structure on the evolution of cooperative behavior. Conclusion. Presenting players' strategies in game theory is one of the factors which affects the player's performance significantly. In other words, we have analyzed the characteristics and the underlying structures of existed types of automata. Consequently, we have explored the application of automata in game theory. However, this study reveals that only few types of automata have been utilized in game theory. We found that finite automata have been widely used to represent simple agents' behaviors. On the other hand, adaptive automata and cellular automata are mainly used to represent complex agents' behavior. The complexity level of both adaptive and cellular automata is determined by the number of states in the automata. The more complex states we have, the higher the capability for the automata to handle more complex strategies. Thank you, one and all.